right, so as a reminder of where we started, or where we finished last time, we started talking about the quantum mechanical model of the atom, basically a new approach to understanding how the electrons are orbiting the nucleus that takes into account the wave of the electron, right? This is the matter wave that de Broglie thought about with his de Broglie wavelength. And so with that in mind, what we're going to start to do is start to utilize this really qualitatively for the most part, but there's one other thing we have to do before we get into the qualitative nature of this, because the quantum mechanical model was pioneered by a number of scientists: Heisenberg, de Broglie, Schrodinger. We've talked so far about de Broglie and Schrodinger. And so the next thing we're gonna look at somewhat briefly is what's known as the Heisenberg uncertainty principle. Now, this is a principle that comes out of a bunch of the math. Remember, we're talking about mathematical models of how the electron moves around the nucleus of an atom. Understanding that the mathematical model is dealing with the charges of the nucleus and the electron. And how those particles move with respect to each other. And what Heisenberg what Heisenberg found is that there's this fundamental limitation to how precisely we can know both position and momentum of a particle at a given time. That's the Heisenberg uncertainty principle. And so if you look at the equation here in the middle of the page, the delta x is uncertainty in a particle's position. All right, let's see if we can pick up where we left off here. That was a fast getting kicked out. Okay. So Werner Heisenberg, we haven't really talked about him much. He through his mathematical observations determines that there's this fundamental limitation to how precisely we can know the position and momentum of a particle, where in the equation down or in the middle of this page, we basically have so this is the equation that governs Heisenberg's uncertainty principle, where the delta x is uncertainty in position. So you may say you want to know the position to a certain amount of certainty, and then that's going to affect how certain you can know the momentum of a particle. So this delta x is, we know this range of within what range can we find this particle, and that particle is moving. If it's moving within that range, well, within what range can we know its momentum? And that's the uncertainty in momentum, where momentum is mass times velocity. But we really know, the mass of the electron from the experiments that we've talked about before, right? From that Millikan oil drop experiment and the cathode ray tube experiment based on the charge and charge to mass ratio of the electron. So we know the mass of the electron. So really another thing we can think about is, well, if we know the mass, then really Heisenberg's uncertainty principle comes out to be this uncertainty in position times the mass multiplied by the uncertainty in the particle's velocity. And so if we really think about it, it's the uncertainty in position and uncertainty in the velocity of the particle that are greater than, or that govern Heisenberg's uncertainty principle. And so that'll all be over that'll be greater, that product will be greater than h over 4 pi. And the h over 4 pi is what comes out of the math that Heisenberg does. And so we can just do a quick example problem. This is fairly simple to understand this from a example problem standpoint. It's really a plug and chug type thing. And this observation, remember, this just comes out of the actual observations of and calculations done by Heisenberg. And so it's actually a fundamental property of matter, is this Heisenberg uncertainty So to give an example of this, we have the following. Suppose we wish to locate the position of an electron to within 5 times 10 to the minus 11 meters. So we're trying to figure it out based on this uncertainty. The uncertainty is, right, if it's within this range, right, that's what we're looking at as the uncertainty, that delta x. So delta x for this x is 5.0 times 10 to the minus 11 meters. Okay. So that's a few percent the size of an atom based on, and that's based on the estimated size of an atom. So we're going to estimate the uncertainty and the velocity of the electron according to the Heisenberg uncertainty principle if the electron is moving at a speed. So we're going to say we know the speed that the electron is moving overall, then what percentage of that speed is this uncertainty in the speed itself? And so to model this, we're just using that Heisenberg uncertainty principle where we can say that delta x times m delta epsilon is greater than or equal to h over 2 pi. Okay, and so our value there, we plug in the 5 times 10 to the minus 11. Multiplied by the mass of an electron. So the mass of an electron is 9.11 times 10 to the minus 31 kilograms times this uncertainty in the velocity. That'll be greater than or equal to h, which is 6.626 times 10 to the minus 34 joule seconds over 4 pi. Okay, and so really we're just solving for this uncertainty in the velocity. So the delta epsilon, right, the uncertainty in the velocity will be greater than or equal to 6.626 times 10 to the minus 34 joule seconds divided by 4 pi times 5 times 2.0 times 10 to the minus 11. Oop, I forgot my units there. Those should be meters. Times 9.11 times 10 to the minus 31 kilograms. And so the uncertainty in that velocity will be 1.157 times 10 to the minus 6 meters per second. And if we use our sig figs, we should have 2 sig figs, and that'll be 1.2 times 10 to the 6, excuse me, that should be 6, not minus 6. Doot, there. Meters per second. Okay, so there's the uncertainty, right? So that's the delta, right? That uncertainty is going to be greater than or equal to that value, 1.2 times 10 to the 6 meters per second. And so as a percentage of the overall, you can just say, well, 1.2 times 10 to the 6th divided by 5, actually, so it should say what fraction, right, not percentage. So 5.0 times 10 to the 6th, these are both in meters per second. Okay, the units will cancel out here. We wind up getting a value of 0.24, or if you want to do it as a percentage, 24%. So you can see this uncertainty can be a fairly large value, and actually the size of that uncertainty in the velocity versus the size of the magnitude of the uncertainty in the position, those two things are inversely related. So as you know better the position, the velocity you'll know with less certainty. Okay, that's really all it is. It's just plug in some values and you'll get your uncertainty in position or velocity. Okay. So back to those wave functions. So the wave functions themselves, they're limited largely because of this uncertainty principle. You can think about if you have a wave, right? You throw a pebble into a pond and the waves move away from where the pebble hits because the energy is imparted to the water and it's moving away. What would the position of that wave be, right? The position of the wave, it's really dispersed, right? So, it's not going to give us a very good answer for that. And so the wave function itself doesn't have a great visualized meaning, at least for us. But what we can get out of a wave function is actually if we take the square of the wave function, okay, so the square of the wave function, or psi squared, right? That actually does give us something useful. What that gives us is a function that indicates the probability of finding an electron near that nucleus, or in a point in space around the nucleus. And we call that the probability distribution. Okay, so the probability distribution of the electron is a really important thing for us. And so we're going to sort of think about this from a mathematical standpoint, just on a simple graph initially, a two-dimensional graph initially. And then we'll look at it from a three-dimensional standpoint. So over here at the right, we have this in this box over here, right? We have a graph, and what that graph shows is a value of psi squared compared to the distance. So r would be the distance away from the nucleus. Okay, so just a length, essentially, a measured length. So as the radius or the distance from the nucleus increases, right? So as this distance increases, you start to get a smaller likelihood of finding an electron farther and farther away. Whereas if you look closer to the nucleus, there's a much larger probability of finding the electron. So you can think of the area under this curve as being 1, right? And so if you think about it, that means that you're going to get most of the electrons are going to be nice and close to the nucleus, or an electron will spend most of its time close to the nucleus, is probably a better way to put it. And so how does this really help us? Now, when we think about understanding matter in terms of the Heisenberg uncertainty principle, this whole understanding the position or the momentum of a particle with really only having good specificity for one of those two things, we can think about us mathematically modeling a nucleus, or an atom, excuse me. And so if you model an atom and you're modeling an electron moving around the atom, in particular a hydrogen atom, and hydrogen atom, because it's the simplest of the atoms, is the good place to start. You can think about what it would mean to have a nucleus in this model for the atom, and the electron around it. So if you have a nucleus here on the atom, right in the middle of an atom, and you do this mathematical calculation, you simulate where are those electrons at any given time, right? And you run this mathematical simulation, which we're doing with supercomputers nowadays. Back when Heisenberg and Schrodinger were doing this kind of stuff, they were doing their math by hand, so quite a bit more work, but we have computers do this for us. And so if you stop that simulation, what you'll find is you might find the electron out here, right, compared to that nucleus. And maybe you continue to run that simulation, you find an electron here, or here, or here. And so what the probability distribution gives you is as you continue that simulation, you get more and more dots saying, if you stop the simulation at this point, you expect to find it here. And so the more times you stop it, the more often, each time you stop it, you get a position. More often, you'll have positions that are closer to the nucleus, in this range here, right, than out here farther away from the nucleus, okay? And so what we get out of this is what's called, I'm going to erase these markings so you can really see this, what this probability distribution looks like. What you get from this is this expectation of finding an electron some distance away from the nucleus, okay? And that's sort of, in this spherical volume, you might say, well, if we run this simulation many, many, many times, you get a simulated view like this. And so you have this probability distribution or probability density around the nucleus of the atom where you might expect to find an electron, okay? And that leads us to this other thing that we think about, which is called an atomic orbital. Okay, so an atomic orbital is just an electron density map, just like we talked about up here in this one. And only this electron density map comes from, remember, it comes from this psi squared, right? This wave function, the square of the wave function. And so this probability distribution, because the wave function is a function of three-dimensional space, right? There are multiple ways of solving this wave function, and those multiple ways of solving this wave function will lead you to a variety of different what we call atomic orbitals. And so an atomic orbital is just an electron density map of the volume where you would find an electron with 99% probability, okay? And so this 99% probability is assuming a set of solutions to that wave function, and there can be many solutions. Okay, one set of solutions is what we call the 1s orbital. Okay.
Professor, I actually have a question about the previous example. I wanted to ask you before. So in terms of what the 24% means, so there is an inverse between the accuracy of position and the accuracy of momentum. So what does that 24% mean? That we know the momentum 24% of the time, or what does that 24% mean?
So
in regards to the momentum.
Yeah,
Sorry.
yeah. So basically, going back to so Heisenberg uncertainty principle. Basically, what we're looking at. Remember, that's the uncertainty in the momentum, which is essentially uncertainty in the speed of that particle. So if the particle, it is moving at a certain speed, right? This electron is moving at a speed of 5 × 10⁶ meters per second. And you have an uncertainty of 1.2 × 10⁶ meters per second. Well, that tells you that you have a range where you can potentially find the speed of that particle, the speed of that electron is somewhere, let's say 5.6 to 4.4 × 10⁶ meters per second, right? So it's somewhere in that range is sort of what that uncertainty says, okay? So if the range is very large, right? It says, yeah, that particle is moving really fast, but we really don't know very well how fast it's moving, right? Whereas if you have a small uncertainty, you're like, oh yeah, that particle is moving with this speed within a very small uncertainty, then yeah, you're pretty sure it's right on that speed that you have measured, for example. Does that help?
Yes, and so does that mean if we have a large uncertainty of momentum, does that mean we know the position more because the uncertainty is so large because of the inverse?
Right, that's right.
Is that what I'm understanding?
So, yeah,
so
the better you know.
76%, I'm just saying, do we know the position 76% because it's an inverse, or am I just making it?
It's related to the constants here. So
okay.
What I would say is we don't currently know the exact based on this, I don't have listed the exact size of that particle, right, or of the electron in this case, but it's a few percent. So yeah, I mean, you could basically do the math on it and say, oh, well, if we know the uncertainty in the position, how to put it? So we don't have the position of the particle here, right? Would that be a 20% difference in the position? That I can't answer for you right off the top of my head. It'd take a little bit more prep work to give you a better explanation. So might have to look into that a little bit for you so I can actually put something together to do that.
I guess my general question is just the inverse, is just the relationship of the position and the momentum. Is
Yes,
there
as
something
the
that we can understand from there?
as you know the position more with more certainty, you'll know the velocity with less certainty. As you know the velocity with more certainty, you'll know the position with more certainty, right? Or as you know the velocity with more certainty, you'll know the position with less certainty, right? So these are the two things. So if you know where the particle is, you don't know necessarily how fast it's moving, right? Or if you know
Yes.
how fast it's moving, you don't know exactly where the particle is. And that's just this fundamental property of matter that comes out of this mathematical simulations and done by Heisenberg.
Okay, last question, and I promise. What is a good percentage? Because you're saying 24% is pretty big. So what is the 1%? Like, what's the good percentage to know? Or 99%?
Oh no, that's not really a relevant question.
Oh, okay. Okay.
This
Thank
is
you.
just, yeah, and to some degree, well, you can think about, actually, here's a better way of thinking about this. When you start to look at when does the uncertainty and the momentum become important? Let's put it this way. We're thinking about particles that are very, very, very small, right? If it's you or me, like I know how fast I'm moving and I know where my position is. I'm a very big object though. And so for very small objects, this becomes much more important because the uncertainty in the position and the uncertainty in the velocity of those particles becomes more on the scale of the size of that particle, if you will, right? And so with an electron, it's very, very important. But if you have a human or a baseball or something that you're throwing, that uncertainty is much, much less important compared to the size of the object. Yeah.
Thank you.
Mm-hmm. Okay. So back on into orbitals. So orbital-wise, we're going to have some labels for these orbitals we're going to go through. These orbitals that we look at, remember they're going to be coming from these solutions to the square of the wave function, and it's just a three-dimensional representation of where you would expect to find the electron around the nucleus. And so the first one here on the left-hand side is the 1s orbital. Now, if you see an S, that S orbitals, they're always going to have this spherical shape. But if you were to have a higher energy orbital that had the same spherical shape, this one's going to be labeled a 2s. And that 2 comes from part of the solutions to the wave functions, which we're going to explore in just a minute before we end our lecture for the day. Another solution to the wave function will give you what's called a 3s orbital. Same type, spherical orbital that has a larger radius to it. But there are other shapes of orbitals that we can get as well. And again, these come out of the values that we're going to look at in a minute. This other type of an orbital, which is called a p orbital. So this is a 2p orbital, right? And so this down here is also a 2p orbital, just a slightly different representation, right? That's going to have more of this dumbbell shape, where at the origin of the Cartesian coordinate system is there's going to be, as you can kind of see here, this would be where the origin would be, right in between those two. There's going to be no chance of finding electrons there, or very, very, very small probability of finding electrons there, essentially no probability. And so we're going to find that this type of thing is going to be common among these different types of orbitals, where these orbitals are, remember, three-dimensional representations of solutions to the square of the wave function, right? These probability distributions. Now, when we think about those solutions, we're going to give them some numbers and values, and then we're going to start to, tomorrow we'll dive more into what the orbitals look like and how those orbitals are related to those solutions. Now, the solutions to the wave function are called quantum numbers, okay? So the quantum numbers, there are going to be 4 types of quantum numbers that we're going to deal with. 3 of them are going to be specific about characterizing the volume in which you would find an electron. And the 4th quantum number will describe something about the electron. We'll talk about that 4th one later. So the first one is called the principal quantum number. The principal quantum number is n. It's kind of like, if you remember the Bohr model that we talked about yesterday, right? We had n values for the Bohr model. Those were the energy levels, and it's related to that, right? It's related to the size and energy of the orbital, okay? And so it'll have integer values of 1, 2, 3, etc. Okay. And so a larger n, right, a larger principal quantum number means the average place you'd find an electron is farther and farther out, right? It tells you the radius is larger for that orbital. The second quantum number, the angular momentum quantum number, L, okay, L is related to the shape of the orbital. So the L up here, right, if we think about the L for an s orbital, we'll talk about that more later. L for an s orbital is 0, okay, no matter what s orbital you have. So for the n value for these orbitals, for the 1s, n is equal to 1. For the 2s, n is equal to 2. And for the 3s, n is equal to 3. If you have a 2p orbital, well, n for the 2p orbital is equal to 2. That's what these values, those numbers there tell you. It's the energy level, or the angular, or the principal quantum number. But for a p value, L will equal 1. Okay, and so values for L can range from L equals 0 all the way to L equals n minus 1. So if your n value is 1, there's only one possible value of L, 0. If your n value is 2, well, then L can be 1 or 0. And we'll look at how these come together. And this has to do with the distribution of electrons around the nucleus. You can only fit it's something we're going to find is 2 electrons very close to the nucleus, and a little farther out you can fit 8. A little farther out from that you can fit 18, and so you get more and more electrons as you go farther and farther out from the nucleus. Okay. The third of those quantum numbers that we're going to look at is the m sub L value. That's for the magnetic quantum number, and that's related to the orientation of the orbital in space. And so that's something we'll explore a little bit more as we start to look in particular at those p orbitals. But the values for m sub L can be anywhere from L, okay, to negative L, but it's integer values from L to negative L. So L, if L is 0, then there's only one possible value for m sub L, it's 0. If L is 1, then you can have 1, 0, or negative 1 as values for m sub L. If L is equal to 2, then you can have values of 2, 1, 0, minus 1, minus 2. And so the table over here on the right shows you, based on what n is, what are the possible values for L and m sub L, and how many orbitals does that lead to, okay? And so if n is equal to 1, then you have one value that's possible for L, that's 0, right, because it's n minus 1. And m sub L can only equal 0 because it's integer values from L to negative L. And so that is going to describe an s orbital. And there's only one possible type of an s orbital in any shell, or in any energy level. If n is equal to 2, you can now have 2 values for L. The first value is 0, and it can only have 1 m sub L. The second value is 1, and can only have, or can have 3 values for m sub L. Now, if we look at the 0 is going to lead us to an s orbital, and there's only one type of an s orbital. But you'll notice we have 3 values of m sub L, and so if L is 1, then we're talking about a p orbital. And since we have 3 values for the m sub L, we'll actually wind up with 3 different p orbitals. So in any given energy level, with any given principal quantum number, you can have 3 different types of p orbitals. And then we'll also have d orbitals, where L, as we get farther out, now we can have more and more electrons. And so d orbitals will have a value for L of 2, which gives 5 possible values, right, going from L to negative L. You have 2, 1, 0, -1, and -2. Those would be d orbitals, and there are 5 different d orbitals. And we'll talk about how many electrons you can fit into these as we move forward. You can also have f orbitals. We're going to spend less time on the f orbitals because they're just not as commonly found in most of the chemical compounds that we work with on a daily basis. And so those are solutions, right? They're solutions to the wave functions. They satisfy a wave function for, and this is going to be a key right now. We'll talk about more of why this is later, but they solve the wave functions for the hydrogen atom, okay? And so the series of numbers, this set, if you will, of quantum numbers is a set of solutions to the wave function that describes or allows us to have a shorthand now of describing what type of orbital we would find, in which we would find an electron. And so we'll spend some more time with that, tomorrow as we get into the shapes and energies of the orbitals and start to look at how the quantum numbers are related to the size and shape of these orbitals. Okay, so that's where we'll pick up tomorrow as we start to describe the orbitals and their shapes and energies. And we're going to begin with s orbitals tomorrow.